Today we are going to learn about optimizing model performance with hyperparameter tuning. In this session, we will explore how to use weights and biases for hyperparameter tuning to enhance model accuracy and performance. You will gain skills in configuring and executing hyperparameter sweeps efficiently. Welcome to our video on optimizing model performance with hyperparameter tuning. Hyperparameters are critical components of machine learning models that are set prior to training and directly impact the model's performance. Tuning these parameters effectively can significantly enhance the accuracy and efficiency of your models. In this video, we'll explore the role of hyperparameters, how to set up a weights and biases sweep, and the steps needed to configure search spaces for tuning. By the end, you'll understand how to run parallel experiments, analyze results, and integrate weights and biases with your workflows. Let's dive in.
Hyperparameters are predefined variables that control the learning process and influence the behavior of machine learning algorithms. Unlike parameters, which the model learns from the data, hyperparameters are set before training and determine the structure and functioning of the model. Examples include learning rate, batch size, and the number of layers in a neural network. Choosing the right hyperparameters can be the key to unlocking the full potential of your models. They directly affect the model's ability to generalize from the training data to unseen data. As machine learning practitioners, it's crucial to understand their role and impact on model performance. Weights and biases is a powerful tool for tracking experiments and optimizing hyperparameters. To set up a sweep, start by defining a sweep configuration. This involves specifying the parameters you want to tune, the ranges for these parameters, and the type of search method you intend to use. You can create this configuration using a YAML file or directly within your Python script. Once you have your configuration, you'll need to set up a sweep controller, which manages the execution of your experiments. After configuring everything, you can execute your first sweep to begin exploring the optimal hyperparameters for your model.
Configuring search spaces is a crucial step in hyperparameter tuning. A search space is essentially a defined range of values for each hyperparameter you wish to optimize. Common search methods include grid search and random search. Grid search exhaustively searches through a specified subset of hyperparameter space, whereas random search selects random combinations of hyperparameters to evaluate. Each method has its advantage. Grid search is more thorough, while random search can be more efficient. Consider the computational cost and model complexity when choosing your search method. Balancing these factors will help you set up efficient and effective search spaces. Running parallel experiments is a highly effective way to accelerate hyperparameter tuning. By executing multiple experiments simultaneously, you can explore a larger portion of the hyperparameter space in less time. To set up parallel processing, ensure your computation resources, such as CPUs or GPUs, are capable of handling the workload. Efficient resource management is vital to avoid overhead and ensure that your experiments run smoothly. Additionally, parallel experiments can significantly speed up model training, allowing you to iterate quickly and reach optimal configurations faster. This approach is particularly beneficial when working with large datasets and complex models.
After running hyperparameter sweeps, the next step is to analyze the results to refine your models. Begin by interpreting the sweep results to identify the optimal set of hyperparameters. Weights and biases offer robust visualization tools to help you compare different runs and evaluate performance metrics. Look for trends and patterns that indicate which parameter combinations yield the best results. This iterative process of analyzing and refining is crucial for continuous learning and improvement. By systematically evaluating sweep outcomes, you can make informed decisions to enhance model performance and ensure robustness in various scenarios.
Integrating weights and biases into your existing workflows can lead to significant benefits. It allows for seamless connection to your established pipelines, providing automation and efficiency in tracking experiments. With weights and biases, you can easily monitor hyperparameter tuning progress, ensuring reproducibility and transparency of experiments. This integration also enhances collaboration within teams, as it provides a centralized platform for sharing insights and results. By embedding weights and biases into your workflows, you create a more streamlined process that supports continuous model optimization and fosters innovation within your machine learning projects.
Bayesian optimization is an advanced method for hyperparameter tuning that is particularly effective for complex search spaces. Unlike traditional methods such as grid or random search, Bayesian optimization builds a probabilistic model of the objective function and uses it to select the most promising hyperparameters. This approach can lead to more efficient exploration and faster convergence to optimal solutions. Implementing Bayesian strategies involves using a surrogate model to predict performance outcomes and iteratively updating these predictions as new data is obtained. By leveraging Bayesian optimization, you can handle complex search spaces more effectively and enhance model performance beyond conventional methods. Hyperparameter tuning is not without its challenges, and being aware of common pitfalls can save time and resources. One major risk is overfitting, where a model performs well on training data but poorly on unseen data. Mitigate this by using techniques like cross-validation and carefully managing search space boundaries. Computational costs can also be high, so consider the trade-offs between thoroughness and efficiency. Understand the limitations of your search space and ensure a balance between exploration, testing new areas, and exploitation, refining known good areas. Finally, aim for models that are robust and generalize well across different datasets and scenarios.
In conclusion, hyperparameter tuning is an essential aspect of optimizing machine learning models. Today, we've explored how to set up a weights and biases sweep, configure search spaces, run parallel experiments, and analyze the results to refine models. We also discussed integrating these techniques into existing workflows and using advanced methods like Bayesian optimization. Remember, practice is key to mastering these skills. As you continue your machine learning journey, apply these techniques to enhance your model's accuracy and performance. Thank you for joining us, and we look forward to seeing the innovative solutions you'll create.